Hello, welcome to a presentation on variation in mathematics. So I'm going to start with a very basic question. What is a tangerine? And this question has actually been a question that I've had a conversation with my children over. I didn't understand why they didn't understand what a tangerine is. There's lots of mathematical concepts, ideas and definitions that children we teach don't understand. So explaining this to them and having it start at a very natural starting point and progress through is very important. Maybe we could start with a basketball and the idea that no, a tangerine doesn't have those black lines. A cricket ball might come into idea. It's the right shape, it's the right colour, but a tangerine is something you can eat. So now we've lost our shape. I suppose a tangerine isn't a perfect sphere anyway, but that's a carrot, not a tangerine. A tangerine is a fruit. So we could come up with a pumpkin. And a pumpkin does look an awful lot like a tangerine, especially when its size has been changed. But a pumpkin doesn't grow on a tree and has quite a lot of different properties when you try and eat it. So we're definitely looking for a fruit, even though the seeds are on the inside. It's not. Perhaps an apricot, and you could explain that quite simply by cutting the apricot in half and noticing there's a stone. So we're looking at this tangerine in lots and lots of different ways, and most of the ways we're looking at it are actually what it's not. These things are not a tangerine, and why, and we're trying to articulate reasons. So a Sharon fruit or a persimmon, that's not a tangerine. It has a sweet flavour. It's definitely a fruit, and there's not a big stone in the middle. But a tangerine is a citrus variety, and therefore perhaps you could say something which has a thicker peel, or you have more acidity in. Finally, have our tangerine, or do we? Why might that not be a tangerine? It looks an awful lot like a tangerine, but I'm sure we'd kind of very quickly establish the idea that that might be an orange. Maybe we could look inside. Is that helpful? Are there comparisons we could make between orange segments and tangerine segments? Have we ever done that taste test? What about if whether it's an orange or a tangerine, it's presented as juice? Is that suddenly, as a drink, does that stop being tangerine, or does it stop being orange? Maybe, again, people who might have had the conversation why this is not orange juice. But why is it not orange juice? It's the same colour, it looks the same. And again, conversations can be had and conversations should be had. Just like in our maths lessons, questioning is absolutely important in trying to develop what things are, what things aren't, and to develop understanding. Maybe that is the way forward. Having oranges, having tangerines all together, and making a size comparison and actually looking at various properties of them. Again, maybe you could argue, could one of them be a satsuma or a mandarin? There are other small citrus fruits. So as we go deeper and deeper in, we need, with our definitions, we need to use better language to compare things. We need to be more precise, and we sometimes need to be more formal. For those that are interested, they're generally smaller and sweeter than oranges, a little flatter in shape, and they have a thinner, looser skin that makes them easy to peel. Tangerines are a specific type of mandarin orange. They are bright orange colour, slightly tougher skins, and their flavours a little less sweet and a bit more tart. Clementines are a smaller type of mandarin orange. They are super sweet, seedless, and have red-orange skins that are smooth and shiny. The mandarins you see in grocery stores are called cuties, and sweeties are clementines. These are easier to peel than tangerines, but not as easy to peel as satsumas. And I could go even deeper. 3 ancestral species are still grown: citrons, citron media, mandarins, I'm not going to carry on there because I will start to bore people, and you can look that up yourself. But the idea is there that at some point we need to stop with our mathematics also, because that's not the definition that is appropriate for the student at that time. We need to know where that is and how that's going. So, back to variation in mathematics. Teachers, to some degree, do it anyway. Variation in teaching methods is good practice, and it's instinctive in a lot of cases. Lots of textbooks already include variation, but many do not. Being overtly aware of when we use variation and how we could use variation will encourage us to use it more often and use it to greater effect. To put a historical context, Deans first mentioned it in 1971, and then it was developed in China and Hong Kong, and it was used effectively then. Mark McCourt put some research into it and says the translations that came back to the UK weren't used effectively, and it wasn't used in our national planning documents at all. Watson and John Mason in 2006 broke it down into procedural variation and conceptual variation. I have a lot of respect for the work of John Mason, and I think he really has done some wonderful things for mathematics. To kind of come slightly more modern, varying the conditions of a problem, varying the method in solving the problem, and varying the problems a method is being applied to. That's how it can be broken down in a very kind of simple sense. And if you look at those 3 things very carefully, you will be very aware that you do those anyway. Vary the problems a method is being applied to. We develop our work in small stages. Most exercises, they start easier and they get more and more complex. There's some variation happening there. And we do use a multiple number of methods to try and help students to understand mathematics, especially using manipulatives and trying to help them understand the structure of a problem, being able to see it in different ways. So coming back, and I apologise at the simplicity of my starting point with it, but I am going to develop this idea as far as I can. So what is a square? And again, you'll notice very young children, they know what a square is, quite a simple thing. So they don't know formal definitions, but they can see a square and say, that's a square. They should be given different contexts of a square so they don't have misconceptions. So something coloured in red in this case, is that still a square? Yes. And good questioning immediately helps to that idea of why. And maybe from a very young age, students will start to say that the sides are the same length, and they may even make inferences about the angles that are there. But they have this idea of what being a square is, and this idea needs to be built and developed. And it needs to be built and developed right the way up through secondary school. Maybe changing the size of something. Some people do have misconceptions that you change the size of something and the shape changes. Perhaps some language could come in here of similarity, perhaps the language of congruence. While we're using variation, we're using language, we're using correct language, we're paying attention to details, and that discussion, that questioning, that dialogue is all part of the experience and the learning of students. Now this is a big bugbear of mine. As a parent, I remember little books which called this a diamond, and it took me a very long time to really persuade my children that this was a square. But changing the orientation of a shape does change the way people see it. How often do we draw squares? Always with the horizontal line of the square being horizontal with the book and parallel to the book. Same with triangles. We often draw triangles as right angle triangles or isosceles triangles. Do we draw them upside down by default? Not that a triangle needs to be defined as upside down, because it's still a triangle, but people and students do use that definition. That's an upside down triangle. We apply things to life. We can ask questions. Do we know it's a square? How would we know it's a square? I suppose at some point formal notation needs to come into it. What do those dashes mean? What do those little right angle marks mean? But we're developing the idea of what being a square is. We're perhaps talking about the edges using slightly more formal terms. AB and DC are both edges. The angle ABC is a right angle. But using the correct terminology and growing in our understanding of. We include this in our Year 7 curriculum because it's something that's not often understood well at primary school, but the diagonals of a square. The diagonals of a square are of equal length. There's more and more richness, more and more understanding. Needs to be taught somewhere. The discussion needs to be had at some point to try and understand more and more and more what being a square. Perhaps the idea of parallel sides, that needs to be introduced at some point. Perhaps the idea here that the diagonals are perpendicular. Again, we've got more rich language coming out. But that is a fact for a square. The diagonals will always be perpendicular. We can put a square into different things, and perhaps very early inferences on circle theorems can come from this, drawing a square in a circle, which we could actually give it a name as a cyclic quadrilateral now. But seeing how that looks and how the diagonals of that square look to be the diameter of the circle. Seeing it in different ways. Perhaps we could give examples that are more open to not being right and wrong. We don't do that a lot in maths. Is this a square? Well, clearly it's not. Why is it not a square? We could talk about dimensions and different dimensional spaces. Are there any squares there? And obviously we can talk about then the faces. To say that a cube does have square faces. Is this a cube or is it a cuboid? We can add that to the discussion. Can we tell? Is there any indication mathematically to indicate it? Is that a square? Well, obviously not, but is a square got any other features? Is a square part of a family? It's part of the quadrilaterals. It's a polygon. A circle is not a polygon. Again, we've got here a diamond shape again. But is this a... We did one just like this earlier on, and that was a square. That was quite early, but this one... What would we have to measure to know whether or not it's a square? Or is it a rhombus? What makes being a rhombus different to being a square? How can we articulate that? What about this? Does a shape have to be closed? Or can there be parts coming out? Is there a square in the diagram? What about this? It might have four sides the same length. I suppose we can't talk about the angles there, but these are good conversations to have that make people think, that make them talk, and hopefully develop an interest. What about this? There are four sides. I mean, they're obviously not the same length. Could we argue that's a rectangle then? What do you need to be a polygon? Is this a square? Why is it not a square? Clearly, giving examples which are not the case and allowing students to articulate why that's not the case is a very important skill. Square has 4 vertices and 4 edges and 1 face. True? False? Is the language the way it should be? The square has how many lines of reflection? Has rotational symmetry of order. The students understand rotational symmetry at that point. Is there an opportunity to connect this to other things? Or is a question like that actually just going to go off topic and lose the variation that we're trying to include? Perhaps that's a similar question. Do we want to talk about dimensional space at this point? Can we express a square in 3-dimensional space? We obviously can in 2. What about 1-dimensional space? What is 1-dimensional space? Can a square exist? Perhaps those are conversations that are not appropriate. Perhaps at some point they are appropriate. A square is a polygon, we know that. Is a quadrilateral. Quite happy with that. Is a square a trapezium? And how do we define a trapezium? The common definition of a trapezium is that it has 1 pair of parallel sides. So a square does have 1 pair of parallel sides, so a square must be a trapezium. Is a square a rectangle? Well, the common definition of a rectangle is that it has 2 sides the same length, another 2 sides that are the same length, and 4 right angles. Those 2 sides that are the same length are opposite each other. A square is clearly a rectangle. The diagram here is a really useful diagram in defining what a square is. Obviously, this isn't the type of diagram that would be appropriate for students in primary school, but we rarely have anyone argue that a square isn't a polygon or that a square isn't a quadrilateral. But there's a lot of resistance to say that a square is a trapezium or a parallelogram. And looking at features of things very, very carefully and understanding them along with the most common definitions we use in this country is very good to develop mathematical understanding. A kite has diagonals that are perpendicular. Therefore, so does a rhombus and a square. So the definition of a kite is perpendicular diagonals. An arrowhead's perhaps a special case of that with a reflex angle, but a rhombus is therefore a kite, a square is therefore a kite. A parallelogram has angles that bisect. Therefore, so does a rhombus and a rectangle and a square. That's a feature of the diagonals of all of those shapes. They bisect. They have midpoints that meet. A rectangle has diagonals that are equal in length, and they bisect. Therefore, so does a square. A square has the additional property of having perpendicular diagonals, so they bisect and they're equal in length, and those are all the properties that define a square. What about an isosceles trapezium using the properties of diagonals? Why is a trapezium not always a rectangle? The usefulness of having robust understanding in these things goes beyond shape. It defines and forms a basis for fluency, understanding things such as mathematical sets, and it develops an appreciation for having rigorous definitions. Students might be interested to know that the definition of a trapezium or a trapezoid in America is different to how we define it. They use it as an irregular quadrilateral. So different words are used, but understanding key ideas are there. And students find this particular understanding very useful if they've got a coordinate geometry question and they're trying to, for instance, prove given 4 coordinates that a shape is a parallelogram. Well, they can look directly at the diagonals and see if they have the same midpoint. Quite a simple process, a lot easier than looking at all 4 lines and seeing do they all have 2 pairs of parallel lines. But understanding these things, delving deeper into them, that's what variation allows. In order for pupils to become creative mathematical problem solvers, it is necessary that they gain the motivation to want to pursue mathematics and persevere when faced with intractable problems. Motivation, that is the very desire to continue and go further, is greatly enhanced when pupils are successful and confident. And that's a quote from Mark McCourt from Teaching for Mastery. But variation does give us a point, almost a hook point, where we can start at a point where pupils understand and push that idea more and more and develop it further to try and develop a deeper level of understanding. Using variation often starts at a point that one is familiar and recognizable for students and progresses to something more abstract. Generalization, that's often where we're trying to go with variation. Perhaps something a little different, but showing students what a radius is by finding examples of what it is not. Maybe one example where there can be some discussion. Is a diameter really just 2 radiuses? According to ASCU in 2011, variation helps us to better focus student attention. Awareness has a structure to it. By this we mean that the amount of sensory data that we are subject to cannot all be dealt with at once. Some things have to be in the foreground of our awareness, others will not. We must try and help learners focus their awareness on critical features. So we have 4 key messages to remember when it comes to variation, and I'll come back to these a few times over the presentation. The central idea of teaching with variation is to highlight the essential features of a concept or idea and vary the non-essential features. Sometimes by showing what it's not, we vary the core feature. But usually we show lots of different contexts where that is the case. Variation is not the same as variety. Planning examples and exercises is key. And I really want to stress that I think there is a real place for variety. I think mixed revision, exam revision, when you want lots of different questions which will make students think differently. But if you're trying to tease out an idea, to tease out an understanding or an appreciation, variation is the way to develop that. Variety is not. When giving examples of a mathematical concept, it's useful to add variation to emphasize what it is and what it is not. So if we're overtly planning something with variation, that will be in the foreground what it is again, what it is again, and then what it is not. Misconceptions are key to it, and teaching students about key misconceptions is part and parcel of being an effective teacher. When constructing a set of activities or questions, it's important to consider what connects the examples, what mathematical structures are being highlighted. Students are encouraged to avoid mechanical practice and instead to practice the thinking process, intelligent practice. I listened to a podcast recently that was quite interesting, and it highlighted a key way of evaluating lessons slightly differently, and it's how much thinking students did in the lessons rather than how much work they did, or did they achieve the objectives, how much thinking. And quite often very able students are the ones who fall short of that, because when they can do something they can move into almost a robotic phase, and that they're not thinking, they're not really thinking, it's just repetitive practice. We often see that with students at primary school maybe, where they have to repeat lots and lots of the same question. And again, there's a real place for practice to try and lower mistakes and to try and develop certain elements of fluency, but that thinking is part and parcel of good teaching and good learning. This is one of my favourite quotes of recent times, I think because I find it challenging. An effective mathematics education system is one that focuses on teaching approaches that maximise subsequent progression rather than pursuit of short-term superficial successes. So at the end of the lesson, I'm not just looking to see, can students robotically do what I've taught them to do at the beginning? Are they ready then, in 12 months' time, to understand it and to be able to still do it? That's a much better evaluation of my success, much harder to think about. Have to think about whether they understand it, not just can they do it in that instance. It also puts a focus on responsive teaching, in that I'm evaluating whether or not I've been successful, whether or not I can move on indeed, by whether or not the students are ready to move on. Are they ready to take that topic further and deepen their understanding of it? So this is the only real task that I'm going to ask you to do during this CPD session, and I would ask you to perhaps pause for however long you need really to have a think about it, but it's to plan a sequence of ideas using variation that would help deepen a student's understanding of the concept of being quadratic. Quite a general, open term. How could this concept develop from year 7? If you teach A-level or A-level further maths, the idea of being quadratic is very much embedded in that curriculum also. So find something that's appropriate for students that you teach on what is it to be quadratic. Pause now. I hope you don't mind me recording some of my thoughts by hand here, because I don't want to sell variation theory as being something that you have to download a presentation on, or you have to find a PowerPoint on, or a worksheet on that demonstrates it. Variation theory could just be having a discussion with students and trying to develop ideas, and your planning might well look similar to some of my planning. I'm sure it will be neater though and much better laid out, but I've started off with expressions. X squared, it's a quadratic expression, 2x squared. Does that change? Do coefficients change something being quadratic? What about adding constants? What about adding a 3x term, a linear term? And then we might start to discuss, well, do quadratic things have to lie under a family of polynomial things? And what are polynomials? How are they defined? Do the signs matter? Discussion can follow, and discussion can follow perhaps at the pace at which the class needs, rather than having a predetermined kind of order on screen. We move to quadratic equations. X squared is 4, and students at a very young age can appreciate what an equation is and what an expression is and how they differ. And again, I've got another equation at the top right-hand side here, which is a quadratic equation that many students perhaps wouldn't be ready to solve at the point when you're discussing what a quadratic is. There are formulas which have a quadratic nature to them. Some formula students might know: E equals mc squared, S equals ut plus half at squared. And if I was teaching A-level and had a mechanics class, I would really like them to see that formula and immediately to be able to say things about the graph, to say things about the characteristics of what will happen with that type of formula, how will it behave over time, and if there was an equation that needed solving, how many solutions it would have. Quadratic sequences don't have to be something that's reserved right till the end of GCSE. They can be generated at a very early stage, and looking at the quadratic sequences and quadratic equations together is a very useful and interesting thing. Identities. We've done equations, expressions. Why not identities? Which identities are quadratic identities? Which ones are true? And perhaps then there's some that could be open to discussion. I don't think it really matters whether we agree they're right or wrong, but I would argue that the first set of fractions, if we rearrange it, it becomes a quadratic equation. X squared is 4. So even though it doesn't look like a quadratic, it will behave like a quadratic. What about y squared equals x? It's an interesting one. At A-level, parabolas are looked at where the x-axis is used as the line of symmetry. That's different to how we normally do it at GCSE. It's in every way just as much a quadratic. What if it's been rearranged as it was below? Y equals x squared all squared? Or we sometimes call that a disguised quadratic, because it's not strictly a quadratic, but when we look at problems at A-level, they often might involve trig functions, but they can be put in a way where they can be factorised and treated like a quadratic. So we don't have to always have definite right or wrong answers, although quite often when we do tasks like that, it questions us as teachers to look at the definition that much more carefully to make sure we really know what we're talking about. We have our first example here where there's a visual representation of what being quadratic is. How does a quadratic sequence, when drawn, visually look different to a linear sequence? We do a unit in Year 7 that looks specifically at that, without finding general nth term formulas through algebra, just looking at the structure and how it behaves. A set of coordinates, quadratic graph. That's another representation of what being quadratic is. Perhaps if the sequence was there, we could look at the common difference of the common difference. Some different forms below. You can see the x squared and then a shift of that graph, but it's still quadratic, and it's developing that idea of there being a completed the square form, which is still a quadratic equation. Perhaps some algebraic manipulation, a bit lower. It doesn't look quadratic quite as it is, but if we do some cross multiplication, we'll get there. Quadratic inequalities. It's a topic at GCSE. It's another part of being quadratic. Quadratic simultaneous equations. It's another element of being quadratic. How many solutions do they have? What do they look like? They're all ideas that can and will be explored, perhaps at the right time. Proportionality. If you divide one thing by another thing and it's a constant, it's clearly directly proportional, but if you divide it by something squared, it's still a constant. We couldn't get away without drawing our quadratic graphs in different orientations, using different axes as being symmetry points. There might be reference to a quadratic formula. Interestingly, that formula is a way to express the solutions to a quadratic equation, so it's valid. Maybe ideas of even functions. When looking at the graphs, can be just an x squared graph, it can be a useful way to move on to some bits of A-level where we use that rule. using the language, like how many roots can a quadratic have? Could define a quadratic perhaps by roots, but is it always the case? Do everything which has up to 2 roots, does that make it a quadratic? Interesting topics of conversation. And then for those people that teach A-level, those are a few things that I thought of. When a ball is thrown in the air, it creates a parabola shape, so it's quadratic. When a chain is fixed between 2 fixed points and hung, now is that quadratic? It seems to look a bit like it. Perhaps those who teach further maths might disagree. Perhaps a more formal definition of a quadratic, the parabola is the locus of the points that in plane are equidistant from both the directrix and the focus. Perhaps you could attach that to real life situations like asteroids coming into the solar system and taking a parabolic motion around the sun. And that is the way I believe that we often go from the moon back to Earth. We traject ourselves round the moon so that we can get back to Earth. And there's obviously the root section, so there's lots of depth that quadratics can be looked into, and I hope some of that is useful. And I'm definitely not advocating you do all of it in one go, but little bits of variation to try and develop that understanding of what it is, not just here's how we solve a quadratic equation, here's how we factorize a quadratic, here's how we use the quadratic formula, and keeping them all as standalone topics. So obviously we want what it is not. Now those things wouldn't just be at the end, they would be put in at various points. So I think the obvious right at the beginning is when we were looking at what a polynomial was, having that reciprocal term added. What about the 1 over x squared? It's definitely not a quadratic. Equation of a circle. Perhaps an ellipse could be mentioned as well, or a hyperbole. Those people that teach further maths would look at the hyperbolic functions a little bit and notice that one of those looks very much like a parabola, but it's not because it doesn't follow the formal definition of a parabola. But there's lots more depth that can be looked at. And again, linear sequences, to go back to something much more simply, that might start out looking quadratic but are not. How do we really explore that? So those are just my thoughts, and I hope that you've come up with ideas of your own. This is certainly not meant to be exhaustive, but this is how you could potentially try and plan variation into lessons yourself without trying to download resources or find extra information. In order for pupils to become creative mathematical problem solvers, it is necessary that they gain the motivation to want to pursue mathematics and persevere when faced with intractable problems. Motivation, that is the very desire to continue and go further, is greatly enhanced when pupils are successful and confident. And that's a quote from Mark McCourt from Teaching for Masters. Here are 3 exercises, and this has been presented by in one of John Mason's books. They're all absolutely perfectly fine exercises, and they are all perfectly fit for different situations. So you may want to pause for a moment just to think what would be the most appropriate one when you're first introducing the topic. Pause now if you want to have a bit more of thought over it. In the first exercise, the variation of signs is controlled so that all possible pairs occur, but numbers and relative values vary, and there is little apparent system even in the variation of signs. A diagram would add a little sense to the variety that is produced, and it is not clear that the concept of gradient as a slope property would be the focus of attention. It is more likely because variation is in the signs that subtracting and dividing directed numbers will be the focus. So by doing that first exercise, we will give good practice to students. It will be varied practice, and directed number will be one of the key areas where they start making mistakes. Will they understand any more about what gradient is as a concept? In the second exercise, there is a selective practice of various possibilities, followed quickly by an invitation to write gradient as a formula, expressing a generality that the learner must already know in order to do the earlier questions. This is then followed by questions about special cases of the formula, so that we can see the author is intending generalization of gradient calculations to be the focus. The last exercise, variation is tightly controlled by only varying the x-coordinate of the second point. Some have found the third exercise too constrained for the development of technical fluency, even boring, while others have found that it is the most interesting of the three because it invites questions and further exploration and includes a little shock that does not yield to an algorithmic approach. The focus is on varying the gradient in a controlled way, so the gradient changes from being a name for the answer to the calculation to being a relationship, to being a property, and also to an area of conjecture by asking the highly mathematical question, what changes and what stays the same? And by examining the nature of the changes offered, we can be precise about what exercise together with the established way of working, collection of social practices affords the learner and with what constraints. Each of the exercises above affords a different kind of generalization, and learners' engagement with gradient as a concept will be influenced by what they can easily generalize from the exercise. I've read out there from some of John Mason and what he believes on it, and I think it's very intuitive, in as much as we often just select exercises fairly randomly, but making sure that what's in the exercise is what we want students to be thinking about. And that might mean using a variety of books, making our own resources, or writing our own questions. There is certainly a place for lots of different varied questions just to see if people have mastered the idea. But in terms of the actual teaching of an idea, teaching of a concept, that's far more difficult to do. And I would argue that I very much agree that the concept is there. I think we've all taught a topic like this before, and students have been able to do it. But if we asked honestly, do they understand what gradient is? The answer is possibly no. The central idea of teaching with variation is to highlight the essential features of the concepts through varying the non-essential features. I think that is one of our kind of takeaway themes from today. So I really want to put some in place and how we can teach things. Again, we wouldn't need a worksheet to do this, but by teaching people what a prime number is, choosing our examples very carefully enables us to do that. We can quickly see one does not contain two unique factors. What do we do with the half? What do we do with -1? Perhaps the method of giving a formal definition right at the beginning, a prime number is a number that has exactly two factors, one in itself. Perhaps that may not be the best way to actually get students to understand what a prime number is. Choice of examples might be the key. There's an area where I've used variation a little bit recently, something I'm trying to consciously do more, and that is in my teaching of circle theorems. And I often see that although I've explained the theorems, talked about the spins, and I'm very happy with kind of how I derive them and how we go through them, showing examples, different examples that look different, but they are the same theorem, and then an example that's not true. I found that very useful. Also notice where I've actually drawn the angle line there. I could have extended it right the way to the tangent. But that understanding by showing what it is again, and then what it is not. I think that's a very powerful tool in helping students understand and deal with misconceptions. Again, examples like this, they often might use ideas of corresponding and alternate angles, and I've seen that used in all kinds of features where lines are not parallel. Example, people often, for the circle theorem, the angle at the centre is twice the angle at the circumference. They don't understand it as that, they understand it as the one that looks like an arrowhead. So if you've not got the centre involved, they immediately come to that conclusion. Or if their lines cross in any way, shape or form, it suddenly doesn't look like they're familiar with, again, what it is again, what it is not. It's very important in teaching, very easy to incorporate into teaching as well. Again, I've seen examples like this countlessly mentioned as it's the one with the cyclic quadrilateral, and so the opposite angles must equal 180. But the idea that, no, this is the angle at the centre, so if I want to work this angle out here, I'm going to have to work the angle at the centre out first and come to that idea. What it is again, and then what it is not. And lots of visual representations of that. Barton, and I think he has the most comprehensive set of exercises and worksheets and resources on variation, says my choice of examples and exercises is the single most important part of my planning. And I personally would argue that should be the most important part of all our planning, what examples we give, how we model them, how we describe them. But our planning is very important if we're going to use variation effectively. Here's just one example, and I just went onto the website and downloaded pretty much the first one I found on a topic that I've seen some of my students struggle with, and I think it's very interesting how he uses variation here and the quality of how it develops an idea so that students can finally get onto something that's quite deep and abstract. And I'm not saying that I would necessarily print this and give it to the students as an exercise, but more so as a way of me developing my modelling in a questioning and example in class. I think there's an awful lot there. So you can find a lot more on variation. Obviously, for all resources, you have to take them, think about them, and ask yourself, is it appropriate to my students? Is it a high quality resource? But there are resources out there which help develop variation. Variation is one of the key themes for maths mastery. So there's lots of resources available from the NCETM. A lot of their resources have, and the maths mastery are looking at textbooks, and very interestingly, all the textbooks in the country, there's a kind of a proforma which says whether or not they satisfy mastery conditions, because lots of textbooks were claiming to be mastery, and I believe only 3 textbooks did actually meet those, and I'd never heard of any of them. No book seems to have everything. It doesn't seem to contain everything we need. We have to be selective. We have to choose what is appropriate for our students, and we have to find the very best of what's out there and incorporate it into our own practice. Finally, if there was any screenshot that you were going to take about what variation is and how we plan with variation, it's on this last slide, so I will leave that up, and I hope that you enjoyed the presentation, and I would very much value your feedback and thoughts. Thank you very much.